So there's the recording started. Welcome to the Winds and Currents webinar. Today we have Ted Strub from Oregon State, who's going to talk about characteristics of poleward pathways between the Northern and Southern California current system. I'll let you take it away, Ted.
Okay. Well, thanks very much for inviting me to talk. I should thank Melanie for volunteering if she's out there, volunteering me, that is. Okay, so you can see a list of the people working on this. Top row is the people on our NASA grant, and the bottom row is all the other people, including zooplankton experts that are working with us. And we're looking at the poleward pathways between the Southern and Northern California current system, which is supposed to go equatorward. So how do things get poleward? So on this slide, I've just given a few examples of the kinds of pathways, trajectories. These are 2-month trajectories of several different parcels that are going north, and the winds are shown for the second month of these trajectories. And so in general, the parcels go against the wind during summer, and that's an interesting thing. We're trying to look and see how they do that. Okay. So the motivation really comes from observations off of Oregon and Washington of unusual zooplankton species, water properties, that are often called subtropical or tropical even. And this infers that parcels, water parcels that come from a long distance from the south. So the natural question is, from how far south can passive water parcels travel and reach Oregon, Washington in a single year? These are often observed during El Nino years, and so the supposition is that they've come during a single year. Okay, can they come from Southern California, Baja California? Can they come from the equator? Okay, and the answer to some of those questions is going to be yes, and then others is no. And then if there's interannual variability, because these observations occur only some years, are they related to the ENSO or the marine heat wave or long-term climate changes? Specifically, can water parcels come from the Southern California Bight or Central California? The answer to that's going to be yes. Farther south, and the answer is going to be unlikely. And what are the seasonal and spatial characteristics of those trajectories that reach Oregon? How does the Ekman transport modify the geostrophic trajectories? So we think of two layers. One is the Ekman layer, and the other is the geostrophic velocities beneath the Ekman layer. And then how does the inclusion of smaller scale eddy diffusivity modify the trajectories? Because we are using gridded altimeter velocities, which are gridded on a 1/4 degree grid. So realistically, we probably don't resolve scales of motion less than, say, 50 to 100 kilometers. 50 is pushing it. Okay, and how does this relate to Odyssey? A little bit of relation is provided by the fact that Odyssey is going to be looking in the Ekman layer. So I'm going to show you the difference between the Ekman layer and parcels beneath it in the geostrophic layer. And how does eddy diffusion or smaller scale, submesoscale motion affect those trajectories? And okay, on the left is some of the plethora of articles that have looked at the arrival or the transport everywhere from Baja California to California coast, Northern California, Oregon, and the Gulf of Alaska. Okay, so one paper that I'm going to use the results from is one that Jennifer Fisher and I helped Bill Peterson write. And this is using the observations off of Newport, Oregon, and I'll show you where that is in a minute. Okay, at the top, this figure shows the ONI index, the Ocean Nino index, which is really just Nino 3.4 smoothed. That's the line, and the PDO is in the bars. Okay, and then beneath that, we see the anomaly, so the seasonal cycle removed, of copepods, zooplankton coming from the north, copepods that come from the south, southern copepods, warm water copepods, and the species richness, which is high for the warm water copepods and low for the northern copepods. So there's a lot of of similarity between these two plots. The zooplankton people like the species richness, and the non-zooplankton person here doesn't see that much difference. So the important thing is going to be, do these southern copepods, do they correspond to passive advection from the south? And we're going to be showing that. Okay, methods. So we use daily altimeter-derived absolute surface currents with the parcels software, and we calculate trajectories for passive water parcels started at different latitudes. We use both forward and backward tracking. So we track forward from the south and backward from the north. And diffusion can be added to the trajectories, and I'll describe that later. We're using the altimeter data from 1997 to 2020. The earlier altimeter data, the coverage is not very uniform. We are looking at just using the plain absolute velocities that of the all satellite data set, which uses all altimeters possible. The two satellite data set, which restricts the analysis to two satellites to try to keep a climatological consistency. And I'm not going to show results from a different data set that blends the tide gauges with the altimeter. And we're using also the OSCO data set, which adds an Ekman component, a 30-meter upper ocean average of the Ekman transports to the geostrophic velocities. Okay, so remind ourselves that when we look at altimeter data, we're looking at this little difference here, this little h, between what the altimeter measures, the height, and some reference ellipsoid. And that includes the geoid and the dynamic height. And so we have to subtract the long-term mean that gets rid of this huge geoid. The contours are 5 meters here in this geoid, but it gets rid of the mean circulation as well. So we have to add back a mean circulation. We are using the French CLS lab mean dynamic topography. We started with the MDT 2018 version. More recently, we've switched to the 2022 version. I'll show older figures that use the 18 and newer figures that use the 22. Okay, here on the left, in fact, is the MDT 22 geostrophic velocities. They go along with the heights. And this is just to orient you. This is the US West Coast, of course, Southern California bight in the south, Central California, Northern California, Oregon, Washington. We're going to be releasing forward trajectories from 35 and 32 north, so deep in the Southern California bight or just north of the Southern California bight, and from 44 north or the actual Newport sampling lines where they sample the zooplankton. Okay, and I think of this as kind of the Pacific Northwest, a large Capes region somewhere between Point Arena and the top of Cape Blanco at 43. So those are 39 and 43 north. A region off Central California where there is a poleward inshore countercurrent that is very important. And then the Southern California bight where there's a cyclonic circulation. And okay, the point is, okay, this inshore countercurrent I'll show is present most of the year. And then in fall, winter, the currents, in this latitude range become poleward. And so for some period of year, there's a continuous flow, poleward flow from Southern California up along the Oregon, Washington coast. Okay, this is the, think of this as the long-term mean. This mean dynamic topography is better or worse in different parts of the global ocean. And in the California current, we think that it's pretty good because of the very large amount of data that we have. The mean dynamic topography is an inverse solution assimilating the drifter data that's available, the hydrographic data that's available, the satellite gravity field to get rid of the geoid, and excuse me, and altimetry data. Okay, so you see the equatorward flow going around the Zeta Bank, the Cape Blanco, leaving the coast and meandering through the core of the California current, eventually in a geostrophic flow entering the Southern California bight. Okay. So what do the trajectories look like if we trace them forward from 32, so down in the Southern California Bight, or 35? And what we're doing is releasing parcels on a 4-degree wide transect every 0.2 degrees. So there's 20 parcels released every other day continuously in both of these locations. Okay, here are some example trajectories, and one of the best years for getting north, starting in the Southern California Bight at 32. And what we do is here, just so we can visualize these, we show the trajectories from the 6 most successful parcels in getting north. Okay, so point here is to show that if you start in the Southern California Bight, okay, this is with the geostrophic flow, this is with geostrophic plus Ekman. If you start in the Southern California Bight, you meander around for a while, and eventually the parcels that are able to get north are entrained into the inshore countercurrent. This bar is, the black bar is 1 degree, the red bar is 2 degrees in wide, and basically showing that the inshore countercurrent and then connecting to the Davidson current is the pathway that is most successful. This slide also shows that if you include the Ekman flow, what happens is these northward velocities occur mostly in fall and winter. The winds are poleward and the Ekman flow is onshore. What happens is you knock the parcels closer to the coast where the velocities are lower, or they make it entrained into lee eddies and other small scale features. And the general result is that Ekman flow decreases the ability of these parcels to go north. So what helps them go north is the inshore countercurrent and the Davidson current. And they travel in autumn and winter. What detrains them from that poleward flow is the offshore jets that occur at the large capes, and the Ekman transport that moves them closer to the coast. Okay, this example starts in the Southern California Bight. What if we start slightly farther north? So here we're starting at 35 north, north of the Southern California Bight. Again, something like 50% of the parcels that get farthest north start within 1 degree of the coast, and 80% start within 2 degrees of the coast. That's just showing the importance of this inshore countercurrent in the south, and which then connects to the Davidson current in fall and winter. Again, when you include Ekman flow, Ekman transport, you move the parcels out of the strongest poleward flow next to the coast, and they don't get as far. They get trapped there. Oh, let's try give them a head start and start at 39 north. Okay, so again, geostrophic on the left, we start at 39 north, and the 6 that get the farthest, eventually get past Vancouver Island. Again, even when we give them a head start, when we include the Ekman transport, they get knocked toward the coast. Here they make it to the Oregon, Washington coast, but they don't make it as far because they get trapped next to the coast. I'm going to skip that one. Go to these is a summary slide from the continuous releases. So each bar shows the number of parcels, and it's a log scale on the left, the number of parcels that arrive at 3 different latitudes, starting when they start at 35 or 32 north. So the 3 different latitudes are shown here in blue. It's showing you the number of parcels that arrived that month at 39 north or went past 39 north. In green, it's 43 north, and in red, it's 45 north, which is past the Newport sampling line. So looking at the green and the red, the most successful. So green is you've made it to Oregon, red, you've made it past the sampling line. And what you see is that there is definitely interannual variability. So let's look at just the geostrophic trajectories that start at 35 north, just north of this Southern California Bight. Okay, most successful in leaving in 97 and arriving in 98. That's a strong El Nino year. 02, 03, 04, 05, some get into the Oregon. 910 is a moderate, and those other two are moderate or weak El Ninos. 910 is a moderate El Nino, and it actually is one of the most successful years of getting far north. 1415 is an aborted El Nino, and it's not a strong El Nino for the winter and moving, but it is one of the more successful years in moving parcels, and we'll look at that in more detail. 1516 is a strong El Nino from the SST point of view, and 1617 is not an El Nino, but this is the marine heat wave period. Okay, is there anything else here? Some of these years, of course, are not El Nino years, so it's not entirely true that these only occur during El Nino years. When you start in the Southern California Bight, very much fewer parcels actually make it to the Oregon or past the Newport line, but it picks out some of the same years. Okay, the most successful years. If we add the Ekman component to the transport, then what you can see, looking at the 30, let's just concentrate on those that leave 35 north, you decrease, as I showed examples of, you decrease the number of parcels that actually get as far as Oregon or past the sampling line at Newport. Okay, there's still some, but much fewer in comparing to just the purely geostrophic flow. Okay, and I'll remind you, the Odyssey will be looking at the Ekman layer. Okay, so that kind of summarizes what we've seen. The one result is that the effect of Ekman transport is to reduce the ability of these parcels to get far north. I'm going to skip this one. Basically, it shows that most of the parcels arrive at 39 or 41 north, 44 or 47 north in winter. Okay, this is just showing the number that get to these latitudes and what month they get there. Okay, so it's in winter they get there, although this shows the same successful parcels in when they leave, the month at which they left these different the month at which they left 35 north. And they can leave from a much wider number of months, but if they leave early, they just mill around and eventually they get caught in the inshore countercurrent and Davidson current, and they get to these latitudes in the winter time or early spring, which is probably a good time for them to get there. So I didn't skip that one. Okay, so here's a summary slide. At the top, I'm showing at the Newport sampling line the temperature at 50 meters depth, 5 nautical miles from the coast. And then the next panel shows a repeat of the anomaly in the southern copepod biomass. So presumably these have been advected from the south. And then I'm showing the results like I just showed, the bar charts, using the ALSAT data set, so using all of the altimeters, the 2 satellite data sets, so trying to be consistent over the time period of the data, and then the Oscar data set, which includes the Ekman transport. And we see again, including the Ekman transport decreases the number of parcels that get far north. There is some decrease when we use pretty much the same years, the kind of marine heat wave years that are where a lot of the southern copepods were seen, 09, 10, 97, 98. Okay, and this period of mild or moderate El Ninos between 02 and 06. So there does appear to be a correspondence interannually with some form of climate variability, either ENSO or marine heat wave. We're not, I'll just leave it at that. Okay, that was going without diffusion. What is the effect when we include diffusion? So the parcels program allows you to include a Magarinsky or several other parameterizations of diffusivity. So this is the parameterization we're using. It relates the diffusivity to the gradients of velocity, and it has a parameter that you specify, and they use in their examples 0.1 for this diffusion parameter. We've tested 0.05, 0.1, 0.15. The patterns remain the same. They do change the pattern slightly from when you do not include diffusion. I'll show that. Okay. So Jessica Garwood told me I should read the paper by Visser, and this demonstrates that if you have a gradient of diffusivity, so you have a region of high turbulence and a region of low turbulence, and Visser was talking about a vertical difference. You could think of this as a jet going this direction with high turbulence and outside the jet with low turbulence. The larger eddies where there's higher turbulence are able to entrain more of the parcels, and so you have a net displacement of mass into the region, excuse me, of high diffusivity. Okay, so we're going to see what happens when we add the diffusivity to our parcel movement. Oops, went the wrong way. Okay, so at the top, we show the same kind of bar plots with no diffusion. So it's pretty much what I just showed you. And you can see again, the years of preferential poleward motion. And from 35 and 32, and let's just look at the 35, releasing north of the Southern California bight. And at the bottom here is when we add our diffusion with a diffusivity constant of 0.1. And what you see is that you do, on some years especially, increase the number of parcels that get farther north. Okay, that's true in 97, 98, true in these middle years of the moderate to mild El Niños. Harder to tell when you get later in the record, but in the 14, 15 period, there are more, and there are more in the 16, 17. Not quite sure. I guess there are more in 15, 16. Okay, so what are these? So I want to look at some of these trajectories to see if we can see what is actually happening there. Are we keeping more parcels in the jet when we add diffusion? Okay, so this is 97, 98. We're looking at the October and November trajectories. The winds shown are from November at 3 different latitudes. And without diffusion, the parcels have meandered around and kind of got moved offshore into the high eddy region. With diffusion, if you only saw this figure, you would say, yes, that's what happens. The parcels are entrained into that jet that's going north, and they stay in the jet and they get farther north. We go another 2 months into the future. Some of the parcels without diffusion do in fact make it up to Oregon, Washington, but many more make it and farther when we include the diffusion. Okay, that would make you think that that mechanism of Visser is working. Here's another example from 2015-16, December, January. This is without diffusion, and the parcels have all followed a single trajectory. Even though some of these are released at different months, but they eventually meander around and get caught at the same time in this single trajectory. Whereas the inclusion of diffusion, what it seems to do here is spread, as you might think, disperse the parcels into more parts of that jet. And remember, we're only showing the 10 trajectories with the maximum extent here. There are many, many more parcels, and many of them did not go north, but these are the ones that we're able to find by dispersing the pathways that took them farther north. And again, more get farther north. If you continue into the next 2 months, that pattern continues. So if we just saw these, we would say, yeah, that seems to be the mechanism. But then we look at 2014-15. Without diffusion, on the left with diffusion. This is July, August. This is September, October. And there may be more parcels in the jet with diffusion, but they all seem to get to the same latitudes. What we have not done, so again, we're only showing you the results of the 10 trajectories with the greatest penetration into the north. What we haven't done is map the density of all parcels that are in the jet. Okay, would we, if we did that, would we in fact see that there, even though these look similar, that there are in fact more parcels in the jet during this period? And we have not done that, but from the bar charts, I'm guessing that the answer would be at least slightly yes. But again, we need to do that. The reason I'm giving this talk is so I can become aware of the things we haven't done that we need to do, and that's one of them. Okay, so here now is our kind of final configuration. We use diffusion, we use the mean dynamic topography from 2022, and these are the parcels using the all satellite data set, parcels leaving just north of the Southern California bight or within the Southern California bight that get to these three latitudes, 39, 43, 45. Okay, and so comparing then to the copepod, southern copepod biomass or the species richness, which is similar, I think we see a fairly good correspondence between the 97, 98, these middle 2002 to 6 years, 09, 10, and this marine heat wave and El Nino period at the end. Things seem to be different after that marine heat wave period, and we haven't sorted that out yet. So there's the result of going forward. Okay, what happens now? So we've kind of showed the importance of the Ekman layer, diffusion, but we haven't answered the question of from how far south can parcels actually come. So here's our picture of the California current again, with the mean dynamic topography velocities. Here's an example of releasing parcels along the Newport sampling line, which you see as a little black dots there. This is releasing them in May and then going 5 months earlier. Here's where the parcels have come from. So there's really, I think of it as 3 pathways to get to the Newport sampling line. One is coming from, and this is 9 months earlier. So 5 months earlier, 9 months earlier. One pathway comes from the west wind drift. Okay. Another comes from somewhere out in the California current coastal transition zone, the high eddy region. And then there is another pathway that comes from the south and may come from as far as the Southern California bight. This is 97, 98, which will turn out to be the year with the greatest, the farthest south that it comes from. Okay, what happens actually if we look at all the parcels? So here I've gone back to what we did using the seasonal cycle of the velocities and releasing every month. So there's fewer parcels, so I can actually show individual trajectories. And this just emphasizes that most of the parcels that end up on the, this is at 44 north, so close to the Newport line, are coming from the west wind drift. And they follow kind of 2 patterns. Well, some come directly, but others, go north and come south in the summer, or go south and come north in the winter, but not very far south. So we haven't gotten further south than 39 or 38. Okay. But some actually do come from the south, and that's what we want to emphasize. Okay, this takes a little explaining. This is backward trajectories, and I've actually there's 4 here corresponding to the parcels that end up on the innermost 9 stations of the Newport line. So that's within 1 degree of the coast. Okay, but I put these in opposite order to actually following them backwards. So this is from March of 2010. We released them in May. We follow them backwards and they come in December, January, they had made it all the way north from 35, 34 north. And they had come to there from within the Southern California Bight. So in 2009, if we go, I've ordered these so that we actually seem to be going forward in time. Okay, so there's a parcel that has come down from the coastal transition zone, Eddy region, and then it goes back north, but others are starting in the Southern California Bight, getting entrained October, November into the inshore countercurrent, making it up through the Davidson Current and ending up on the Newport line. So the farthest they go south is the northern part of the Southern California Bight. That's arriving at the most inner part of the Newport sampling line. We go to the next 1 degree offshore and the Newport sampling line, we see a similar pattern. Okay, going farthest in the past, we start in the northern part of the Southern California Bight, come up the inshore countercurrent, the Davidson Current, and we end up actually overshooting the line and then coming back to the line. So this shows, at least during this year, we do come from the Southern California Bight, but the northern part of it. The two strongest El Niños give two different examples. The 97, 98 parcels start in the southern part of the Southern California Bight. This is the farthest south that we see parcels come from in the whole record. And they eventually find their way, meander into the inshore countercurrent, and then meander, toward where they will end up. This is only in February. They will end up on that line in May. In 2015, it's a little different in that the parcels have come, and they have actually come from out in the California Current Eddy region. They've come and they've circled around Point Conception, and then they've gone back north and made their way back up to the line later in May. Okay, so they haven't gone very deeply into the Southern California Bight. They haven't gone into the Bight at all, actually. This is important because the 97, 98 is the only year where a certain species of the krill that is typical of the southern region was found off Oregon. And people said, well, what happened in 2015, 16? It was another strong El Nino. Well, the parcels just didn't come from the Southern California Bight at that point. Okay, so here we have, okay, I'm going to run out of time. So this is another bar chart, but going backwards in time. And we've divided the Newport line up into 4 1 degree sections offshore, from nearest shore to farthest offshore. If we look just at the region that's about 100 kilometers offshore, and we're showing the parcels that come from 36 north in red, so almost to the Southern California Bight, 39, so at the southern part of the Large Cape region in green, and 42.5, so at the top of the Large Cape region in blue. And the correspondence is not as good, but there is still some correspondence, as there were for the forward tracking, with the El Nino years, these middle years, 09, 10, and then the marine heat wave years. And I'll just see if I can go a little faster here and get done with what I wanted to say. This is showing you where the years where the parcels came from farthest south, where they came from. Okay, so like I say, in 97, we come from far south in the Southern California Bight. 09, we're down in the Bight. 16, which is not an El Nino year, we're in the Bight. Others just kind of move in and out of the Bight. And then there's about 4 years in which we come down, circle around Point Conception, and then go north. So I've answered kind of the question that we asked, which was how far south can these parcels come? And it's really in the Southern California Bight. I wanted to show one more slide for my Scripps friends. So where do parcels that are in the Bight, where do they come from? Okay, do they come from Baja California? And the answer is pretty much no. Here we've used the seasonal cycle of currents, and we've started at 32 north, and we've gone backward for 1 year. And this is my way of apologizing to my Scripps friends, because I've teased them by saying the Southern California Bight is not actually part of the California Current. And why would you make measurements on the Scripps Pier, which is just north of this line, and call that a climate record? Okay, well, this shows that in fact, Scripps Pier is located at a pretty good place to sample these geostrophic parcels that have come down straight from the core of the California Current. This is using the seasonal cycle, which lacks the mesoscale variability. This is using this year that had the furthest south, 1998, 97, starting in 98, going backward. And again, most of these parcels are coming from the core of the California Current or the CTZ region. A few come from farther south. So as far south as Punta Eugenia. They could not actually get to Oregon during this year because they arrive up here in winter. Okay, so here are my answers. Can we bring parcels from Southern California? Yes. From Baja California, it's unlikely in a single year. From the equator, further south, mainland Mexico, no. There is some correspondence between the parcels that get farthest north and the warm ENSO events and the mean marine heat wave period. Mechanism not quite clear. I think the winds are involved, but also the ENSO signals as well. Okay, can we reach the hydrographic line from Southern California? Yes, rarely from the Southern California Bight. How do they do this? They use the inshore countercurrent and the Davidson current, primarily in autumn and winter. How does the Ekman transport modify the movement? It reduces the distances traveled by the parcels. Parcels in the geostrophic flow beneath the Ekman layer may travel farther. And including eddy diffusivity seems to increase the number of parcels that reach the higher latitudes. We can't include diffusivity when we track backwards. It makes no sense. But sensors such as Odyssey that explicitly resolve that small scale motion would allow us to track backward with something like the same effect as the diffusivity. Unfortunately, it will be in the Ekman layer, but that's just the way it is. And I think that's time for questions. Here are some actual drifters to satisfy those of you who are tired of virtual drifters. And I'm done.
Thanks, Ted. This was great. Questions? So maybe while people are thinking of questions, I'll ask, I guess one of the fundamental questions on the biology side must be, is it the ecosystem that's moving north or individual zooplankton, phytoplankton? What's their lifespan?
Right. Okay. So a lot of work has been done on these marrowzooplankton that have to recruit to the bottom. So crab, urchin, other kinds of, and barnacle larvae. They have a finite time, and usually people look at weeks to maybe 6 months. We're talking about, when we're talking about either the krill or the copepods, and this is where the zooplankton people should be jumping in to answer this. They live entirely in the ocean, I mean, out in the ocean. And so I think you can move the whole population, and multiple generations can move. But the zooplankton people should really come in, and quite often when I ask them, the answer I get is, well, that's something we're looking at.
Need for more data.
Yeah. Yeah. Well, they have a much harder job than we do. I should have mentioned that one of the motivations of this is that the copepods that come from the south, the warm water copepods, are poor in lipids and fats. So when the juvenile salmon come out in spring, they want fat copepods. The ones that come from the north are in fact richer in fats and lipids. So it matters if there are years in which most of the copepods are coming from the south. It degrades the survival of the juvenile salmon.
That's really interesting. There's a question in the chat from Jamie Pringle, who says he can't turn on his microphone. He says, I'm curious, when you talk about currents with Ekman transport, what depth would the copepods have to be to experience this velocity? What vertical structure for the Ekman transport are you assuming when mapping the flow to the depth of the copepods?
Right. So the Oscar data set includes, they modeled the Ekman flow and they average over the top 30 meters. So I have to keep emphasizing that we are actually not modeling the copepod transport. Okay, some of the copepods, some of the zooplankton certainly undergo vertical migration. So during the day they go deeper, during the night they come up farther into the water column. We are just saying, is there a difference between parcels that stay in the Ekman layer and parcels that are beneath the Ekman layer in the geostrophic layer? So I think of the beneath the Ekman layer, I think of as 35 meters to 50 meters, somewhere in there. We had, Peter Neeler had moorings underneath a Topex crossing, and we were able to correlate the surface geostrophic velocities with the moorings, and the highest correlation was down between 35 and 50 meters. So the Ekman flow above that was degrading the correlations.
Thanks. Other questions?
So I guess, in thinking about the Odyssey, even though it's in the Ekman layer, will you be able to map diffusivities or submesoscale eddy kinetic energy, submesoscale size, across a jet that occurs either going north or south?
Yeah, that's a great question. I think that for Odyssey, and I see Alex Weinteer's on, so he may want to comment further, but the expectation is that the instrument's being designed to do 5-kilometer postings, and for currents to knock down the noise to something that's really usable, probably that will involve averaging to about 30-kilometer useful pixels. So that's not quite submesoscale, but it may be higher resolution than we're getting currently from products like Oscar. And so I see Melanie has her hand up.
Oh, yeah, I just wanted to kind of elaborate on the question for Alex. Because what Ted might not be aware that the error in the Odyssey velocities will be lower at higher wind speeds. So the situation you're asking about is actually a good situation. And so I'm wondering if Alex has a kind of back of the envelope number in mind for whether that averaging scale that Sarah mentioned might not need to be so large in a situation like the wind-driven jets that you're talking about.
Yeah, once we get up to around 10 meters per second wind, we kind of start to asymptote down on the air, and it flattens at around, well, performance flattens around like 12 centimeters per second, 10 centimeters per second. And then the requirement, we have margin in our engineering. So the actual requirement we have is more like 25 or maybe 20 centimeters per second, which is less than half of the average requirement. So yeah, so the answer is yes, the averaging scale goes way down when the wind speeds are higher. So I don't know if I have a number, but 10 or 15 kilometers probably.
So it could be that you can get snapshots with higher resolution, say during winter storms or during the summer winds from the north, which can be 20 to 25 meters a second.
Yeah, you can get, that's pretty high winds, yeah.
Yeah, our guys have faced 50-knot winds trying to head north from San Francisco to get up to Oregon.
Oh, wow. I was going to ask a related question, I guess, that you've done this assuming a diffusivity, sort of a stochastic diffusivity process. But in reality, of course, the small scale processes are parameterized, and they really should have mesoscale, submesoscale dynamics that aren't resolved. Do you have any sense of what the difference between real velocities and a diffusive representation might be? I guess that's the question we're all after, so you probably don't.
I don't. No, I don't. I have not really been part of the submesoscale
Mhm.
community. I should say that I'm also not part of the Lagrangian community.
Mhm.
There's a whole community of the Lapkod group, who have been working
Mhm.
with the Lagrangian statistics and for a long time. And I think Rosemary Morrow's group also have more expert people on the Lagrangian statistics. So there are people that might be able to better answer the
Mhm.
questions about the small scale Lagrangian versus Eulerian velocity.
Mhm. Other questions? Finally, I was going to ask, at the very end, you showed real drifters,
Yeah,
and I wondered how your statistics compare with actual drifters or HF radar for that matter.
okay. We haven't looked at the HF radar, and
Mhm. It's
but
really confined to the coast, so there are a lot of reasons not to look at it.
right. These are drifters. This from Brink et al. And Zaka et al. Really a lot of some of the same drifters, and these are of course in the Ekman layer. So
Mhm.
one sees, and most of these, the ones from further north, Brink et al. Noted that they really didn't see things going northward. They see things going south, and in the Ekman layer they avoid the coast and they don't go into the Southern California bight,
Mhm.
or at least they don't get entrained there. These are drifters that were released in the Santa Barbara Channel. They get about as far as Point Reyes, maybe Point Arena, and then turn around and
Mhm.
come back. So we wanted to see to what extent our drifters look at all like this.
Mhm.
So these are the geostrophic parcels that are released at 39 north and go forward in time, and they're quite happy to go into the Southern California bight. Kind of, I showed you the opposite of backward from the bight. These are in the Ekman layer. So this is the Oscar data, and they also they like the drifters, they avoid the coast and they avoid the Southern California bight. Some of those actually do go north, and that's part of what we're looking at in both of these cases. So we did this to try to say, do our parcels look like the observed drifters, noting that the observed drifters are all in the Ekman layer.
Mhm.
So I guess that's the only thing I can answer about the drifters. Like I say, most of the drifters that were released in the Santa Barbara Channel, which is part of where we were releasing our parcels, they don't get further north than about Point Arena. But I don't know to what extent they release them at all times of the year in their temporal sampling.
Yeah, that's a great question. They have sort of a short lifetime.
Yeah, in this figure, Jack Barth actually he's a co-author, made this figure. And the dark lines are the first 40 days and the light lines are the rest of the days.
Mhm. Any other questions?
I see Melanie is raising her hand.
Yeah. Go ahead,
Well,
Melanie.
Jamie just put a question in the chat, so I think you should take that one first.
I can read that. Jamie comments, Sutka et al. Has a small north compared to what you would need to answer this question properly, he says.
Oh, I think he means small n, like small number of drifters.
Small n, sorry. Yeah.
Well, that's of course a lot of this work, has been done with models, with parcels, releasing millions of parcels for the benthic invertebrate kind of studies. The PISCO group has done a lot of that, and we don't have those kind of drifter numbers to work with.
I think it is still interesting, though, to show you what's possible in terms of how far they can go, the real drifters. Like John Fram, who is the assistant project scientist or associate at the OOI Endurance Array, told me that they had a mooring that broke free in April off Washington State, and they retrieved it off Ketchikan, Alaska, that October of that same year.
Right, so going up, and we showed, some that go past, much past Vancouver and the Queen Charlotte Islands. I'm not sure I trust the mean dynamic topography as you get farther north and there's fewer data. I wanted to mention, nobody's asking about the poleward undercurrent.
Mhm.
There is a poleward undercurrent, and the earlier question about, say, what depth are we talking about? If you get down to 150 meters or so, then you should be in the poleward undercurrent. And Kirk Collins's group have put floats down in the undercurrent, and it turns out that they have similar poleward velocities to what we see, something like 10 centimeters a second. They also, the median time that they stay in the poleward undercurrent as floats is something like 200, 300 kilometers, and then they pop out into eddies, and some of them go back in and go north. So it doesn't seem like they are more efficient at moving things to the north, but they are another source of a different kind of poleward motion. And some of the zooplankton could vertically migrate down to in the undercurrent. And we can't look at that. We have a modeling component with Ricardo Matano and Vincent Combes, who have run the models, nested RAMS models, but have not done the analysis yet. So there will be more information coming from deeper in the water column from them.
Yeah, I was going to mention something about that, but first there's another question in the chat.
For me to go ahead and ask that.
Sure.
Ali Reza asks, why is El Nino in El Nino years, is the poleward current stronger compared to normal years? Yeah,
well, this is a classical question of, is it a signal that's coming through an oceanic pathway or an atmospheric pathway? And the classic answer to that is that the further north you get in the California current, the more the winds are important. This is a principal estimator pattern between the wind field and the 1 degree averages. So these are Eulerian fields of the altimeter velocities. So this correlates these two, the wind and the velocities, with the seasons included. And this is the time series that goes with it. If you take the seasons out, these are the wind pattern, this is the current pattern, and this is the time series. So say 97, 98, largest signal, is basically saying that during this period, taking the seasonal cycle out, the anomalous winds forced anomalous currents in the northern part of the California current next to the coast. And some of these are El Nino years and some are not. That's why I indicated that we don't know the mechanism, but I think from past work and from this, the winds coming through the atmospheric connection will be an important part. This is hard to explain, but on the left, you see 96, 97, 98. This is coming across the Pacific from the western part of the Pacific to the South American coast. This is sea level in a Hove-Miller diagram. And this is going up the coast of North America. So in 97, 98 was this huge El Nino. And so there was a strong signal that came, and that is also associated with poleward velocities. Okay. And so I'll say that on other years, it's not as strong, but there is a component, and it's stronger the further south you go, of a El Nino signal coming through the ocean. Does that partially answer that question?
Sounds good to me. Melanie, did you have another question?
Yeah, it's more of a discussion prompt, but Ted, do you happen to have a slide with you of Ricardo and Vincent's model domains?
I don't.
But
No.
that's okay. I was just gonna say that this is an ongoing project, and another part, this part that Ted and Corinne have been doing with inputs from the South, focusing on those, is kind of the first part. And then my student, Andrew Scherer, is going to be looking at in more detail the inputs to the Northern California current system from that west wind drift, and also how far parcels can go out to the north during winter, and then whether the same water masses come back or if new ones come from the west the next year, those kinds of questions. And Corinne, who's been doing these trajectories, is retiring at the end of this year. And so Andrew will be kind of setting up his own analysis machinery. And so if people have suggestions about sort of in phase 2 of the project, if there are things they think we should add in or consider or do differently, then suggestions are very welcome, because there's a few years left in this project still.
Mm-hmm. And Andrew will be using the model field, so 3-dimensional fields, that unlike our fields are really 2-dimensional, although I think of the Ekman inclusion as being surface and the geostrophic as being slightly beneath the Ekman layer. So Andrew will have full 3-dimensional fields to look at.
And the model is actually nested within ECHO. So Vincent has been running a 1/12 degree model of most of the Northeast Pacific, and then that's nested down to a 3-kilometer resolution ROMS model that covers the California current system, and it covers the whole altimeter era. And actually, I think he covers the whole ECMW, the ERA5 era.
Yeah.
Well, we are just about at the top of the hour, so we probably should stop. This has been a great discussion. Thank you very much, Ted, for your talk and for stimulating such great discussion. And thanks everyone for participating. I'm going to stop recording.
Okay.